You already know that a rise in electric current can also be generated from an interaction between a magnetic field and electric circuit, right? But do you know how? The principle behind this is called Faraday's law of induction. We are the representatives from Group 2 of Grade 12 STEM 3, presenting to you all what you need to know about Faraday's law.
In 1831, Michael Faraday in London and Joseph Henry in New York independently discovered electromagnetic induction. It is the production of an electromotive force across an electrical conductor in a changing magnetic field. This is the principle behind inductors and transformers, generators, electric motors, and many more.
This video will help you explore the different factors that affect electromagnetic induction. And after this, you should learn how to derive the formula of Faraday's law.
Faraday's law is a fundamental law of electromagnetism predicting how a magnetic field will interact with an electric circuit to produce an electromotive force. And electromagnetic induction is the outcome of this principle. Electromagnetic induction could also be used in calculating electromotive force, and the easiest way to demonstrate this is through Phet simulations. Search the web for the website Phet simulations on Faraday's law, and you can actually see manipulatable illustrations which can be used for electromagnetic induction problems. Here are the few sample situations.
Situation number 1. Using the Phet simulation, move the north side of the magnet into the right side of the coil. Repeat with the south side going in first into the coil. You can see the bulb lights up after the magnet is inserted inside the coil. But what happens as you move the north and south side of the magnet to the coil? Does the needle and the voltmeter move? If so, in which direction? Clockwise or counterclockwise? The answer to the problem is that as the north pole goes in first on the right side of the coil, there's a movement of the needle and the voltmeter at counterclockwise, which means there is a negative fluctuation of voltage. Meanwhile, as the south pole goes in first on the right side of the coil, there is a clockwise movement from the needle and the voltmeter, which means there's a positive fluctuation of voltage.
Now, let's move on to situation number 2. Make sure to enable the voltmeter first, then move the north side of the magnet into the right side of the coil and exit the magnet on the left side. Repeat with the south side of the magnet. Observe what happens. So what happens to the movement of the voltmeter as you exit the north and south side of the magnet of the coil? So therefore, as we move the magnet with the north pole leading the exit from the coil, you can see that there is a clockwise movement from the needle and the voltmeter, which means there is a fluctuation of positive voltage. On the other hand, as we move the magnet with a south pole leading the exit from the coil, there is a counterclockwise movement from the needle and the voltmeter, which means there is a fluctuation of negative voltage.
Problem number 3. Move the magnet into the right side of the coil very slowly. Repeat with moving the magnet into the coil very quickly and notice what happens to the light bulb and the voltmeter. Based on the demonstration that was shown, what happens when you move the magnet into the coil very slowly versus very quickly? What relationship can you make between the motion of the magnet and the current produced? The answer to this is as we move the magnet into the coil very slowly, the voltage also changes slowly. However, as we move the magnet into the coil very quickly, the voltage also changes very quickly and the light bulb lights brighter. As a result, as the motion of the magnet increases, the current produced also increases, which explains why the fluctuation of voltage is more extreme.
Problem number 4. Select the 2 coils option in the simulation. This one. Move the magnet in and out in both coils, like this. Now, observe what happens. What relationship can you make between the number of loops and current produced? The explanation behind this is that as the number of loops increases, the current produced also increases. We can say that electromotive force and number of loops share a direct relationship.
From the data and analysis of the simulation, we can conclude 3 main things.
But of course, if this Phet simulation is not available, and if the given problems include mathematical calculations, you can say that as number of turns or loops in the coil increases, the current increases. The current is proportional to the number of turns. We can also say that the current increases as the rate of change of magnetic flux inside the coil increases, which is represented by d psi over dt. If we were to monitor the resistance of the whole circuit, that is of the coil and the wires in the ammeter, we would find that the current is inversely proportional to the total resistance of the circuit. I equals negative n over r d psi over dt. If we multiply both sides of the equation by r, we get Ri equals negative n d psi over dt. Resistance times the current is a voltage of a potential called the electromotive force. Electromotive force equals negative N d psi over dt. So that's all the fundamental information you need to know about the Faraday's law.
That ends our video. We hope that you'll remember this